right, this section is 2.5, implicit differentiation, okay? And so basically in this section what we're doing is we're saying that, okay, sometimes you're going to have more than one variable. And when you're differentiating, you always differentiate with respect to a certain variable. We've been always differentiating with respect to x. Okay, when we have an equation and it's solved like y equal 3x plus 4, that function we say it's written explicitly, x in terms of y. Sometimes, though, they're not, and if they're not, we could solve them for y. If in this equation, if I tried solving for y, I'd get two equations. I'd get y equal plus or minus the square root of negative x squared plus 36. Not something I really want to do, okay? So there is something else that we can do. We can use what's called implicit differentiation. Implicit differentiation. Said the wrong word. And so what we do is we're kind of doing this like we did section 2.4. If you remember, we did a variable substitution, u, and we did our differentiation with u, and then we had to go find out what the derivative of u was with respect to x. We're going to do the same thing, but we don't have u's here. We're going to have y's that we're differentiating. So it's just a different letter. We're going to treat it the same way, though. The problem is we don't know what y is with respect to the derivative of y is with respect to x. So we're going to end up with dy dx's in our answer. And let's go through this and I'll show you what kind of happens. Here's my function. If I want to differentiate it, the derivative of x squared would be 2x. Now I get to y squared, okay? So I'm just going to put my plus. The derivative of y squared with respect to x, I really don't know what the derivative of y is with respect to x, but I do know this is going to happen. I could drop down my 2 and say it's 2y. And if you kind of look at it, there's some expression that y is equal to. I just don't know what it is. You almost could look like y as being something that was substituted in there for something else. And then you would say, oh, well, whatever that derivative is with respect to x. And this is what we do when we have the x's and the y's. And, x's and y's are just normally what we do. Now, the derivative of 36 on the other side is 0. Normally, what we want to know, though, is what is dy dx, because that's the derivative, isn't it? We don't know what it is yet, but guess what? We can find it, okay? And here's what we do. We solve for dy dx. We could do anything that we've been doing so far with implicit differentiation if it wasn't solved for y already. It's just they usually tell us what the function is. It's usually solved for y. It's called f of x of g x, whatever they call it. So here, if I want to do this, what I'm going to do is just get that by itself. Pretend it's just a great big old variable I'm solving for. So we'll subtract the 2x from both sides. And then that leaves me with 2y dy dx is equal to negative 2x. And then if I want to get dy dx by itself, I need to get rid of the 2y. So I will divide both sides by 2y. That cancels out. And I'm left with dy dx, which remember, that's the derivative of y with respect to x. So we still have our derivative here. It's kind of confusing, but we actually do have our derivative here. It was just a little bit different to get to it. It's negative 2x over 2y. Okay? So if you had a point and you're trying to find the derivative at a certain point, instead of just plugging in the x like we've been doing, we would have to plug in the x and the y, and we'd get it. By the way, doesn't this reduce to negative x over y? So we probably have our answer is just negative x over y. Let me just check and see what the answer key, yeah, this is what the answer key has. A lot of times I like to just make sure they didn't go and simplify the algebra a little bit more. Okay, so I'm gonna do some on video just so there's some out there in case you're absent or trying to work ahead or whatever, and we could always do different ones in class. Number 3 is x to the 1/2 plus y to the 1/2 is equal to 9, and though this is kind of good, they already wrote them as fractional exponents. They didn't give us those radicals that we then had to go write as fractional exponents. So if I want to take the derivative here, I just go term by term and I take it. The derivative of x to the 1/2 would be 1/2 x 1/2. Remember, then what we do is we subtract 1 from the exponent. Well, 1 would be 2 over 2 here, negative 1/2 minus 2 over 2. I'm sorry, it's positive 1/2 minus 2 over 2 would be negative 1/2. Okay. And then now I go to the next term. The derivative of y to the 1/2 would be 1/2 y, and then subtract 1 from the exponent to the negative 1/2. And then I don't know what the derivative of y is with respect to the x, so it's dy dx. Again, it would have been kind of ugly to solve for y here, and so this works great when you get functions like this and the variables are all mixed up and you really can't get y by itself. Now the derivative of 9 is 0. So if I want to get dy dx by itself, I could solve for it. Let me clean this up a little bit because this is going to get pretty nasty. The algebra already could get pretty nasty here if we don't do that. Remember, this is the same thing as 1 over 2 x to the 1/2 plus 1 over 2 y to the 1/2, which, remember, the negative exponent just bumps the thing it's attached to down to the denominator, but the exponent becomes positive. So this is, again, this is an algebra thing that we're running into that we have to remember. Alright, so now if I want to solve, I could subtract this term from both sides rather than I'm going to actually say I moved it from this side and it's over on this side. Remember, I can subtract it from both sides, and one of the ways that we can kind of cut down some of our work that we write down is just to think when I move it to the other side, it shows up on the other side with the opposite sign and it cancels out on the side it was on. So now I have this. I'm going to rewrite it. I'm going to do the next step. I have 1 over 2 y to the 1/2. Okay, so I need to get dy dx by itself, and right now what I have is this. Okay, so I'm just writing it all down again, or copying it. To get it by itself, I need to multiply. I've got a fraction in front of it. And you remember what you do to get rid of a fraction. You can divide both sides by the fraction, but that's the very unfinessed way to take care of it. We can multiply by the reciprocal. 2y to the 1/2 over 1. You'd see that those would cancel each other out and just leave you with dy dx. And when I did it to the other side, you know, it's just 2y to the 1/2, isn't it? I'm not going to write the 1 because I don't need to. All I got to do now is simplify, and I'll have my derivative. I'll have my answer. This is the derivative of that function. The 2's would cancel out because there's one on top, one on bottom, and it's negative y to the 1/2 over x to the 1/2, and since they gave them to me as fractional exponents, I'll just write them as fractional exponents. I could have put negative square root of y over the square root of x, but remember, we're learning to communicate properly in math, and that means give it back to them the way they gave it to you. Okay, this one here is going to get a little bit more complicated, and it's because we have that xy term, and that is we're going to have to use the product property there, I think. Yes, we're going to have to use the product property there. Okay, so if I want to differentiate this, I can't really solve for y here. It gets very messy if you try. Again, that's why we're using this method. So what I'm going to do is differentiate each term. The derivative of x cubed is 3x squared, but now the next thing I run into is this xy. I'm going to go over to the side and find the derivative of xy and just stick it in there because I'm going to need the product property. If you have two things multiplied together, it's the first term times the derivative of the second term, which would be y prime since I don't know what it is, or dy dx. I could put dy dx. I'll just use y prime here just to show you could do either one. And then plus the second term times the derivative of the first term. So that's going to be the derivative of x is 1. So I get xy primed plus y. Now remember, that whole thing was subtracted. You could have tried to do that in your head and kept up with the negative sign, but I find myself, I make too many mistakes when I try to do that. Okay? So I'm going to write that in there. I'll go distribute in a minute. And then I've got to take the derivative of y squared. Well, that would be 2y and then y prime, or I could write dy dx. Again, they mean the same thing. One is just Leibniz's notation. The other is Newton's notation. So we'll try to give fair, time to both of them, since, you kind of do need to know how to use them interchangeably. So what I have now is 3x squared minus xy primed minus y plus 2y y primed equals 0. Okay. The thing about this is I need to get the y prime by itself. Okay, so let me do this. It's here and it's here. Let me let me do a little bit at a time. Maybe that would be nice if I just did a little at a time and kind of got down to it. I need the y prime by itself, right? So why don't we do this? Let's go ahead and move the terms to the other side that don't have it in it. If you look at the solution key, they do it a little differently, but I kind of think this is an easy way to explain it, so I'm going to go for it, okay? I could move the 3x squared to the other side by subtracting it, and I can move the minus y to the other side by adding y. So that's what I'm going to do, and I'll just do it in one step just so we don't have so much, you know, I wouldn't have to go to a new page or anything. So what I have left on the left-hand side is negative x times y prime plus 2y y primed and y prime. Since I moved the other stuff to the other side, it's negative 3x squared plus y is what's over there now. Now, if I want to get y prime by itself, I could factor it out because it's in both terms. That's how I'm going to get it by itself. So I'm going to take out the y prime, and what I'd have left, it's supposed to be a parentheses, negative x plus 2y is equal to negative 3x squared plus y. Okay. Now, I want y prime by itself, so now I'll divide both sides by negative x plus 2y. Negative x, that's a big, bad, ugly x, plus 2y. It cancels out over here, and I have my derivative finally. Y prime is negative 3x squared plus y. I'm going to put it in parentheses and just divide, since I don't think I can cram that below it. Divided by the whole denominator is negative x plus 2y. There's my answer right there. If you check the answer key, what they do is they'll probably switch. They probably won't lead off with those negatives. So like on the top, they will probably write y minus 3x squared on the top, and on the bottom they'll write 2y minus x, just because that is, you know, people don't like seeing negatives right off the bat. And I'm being a little rude by leaving it that way. It's just I'm out of space on my iPad. I'm also out of time, so I'm going to leave it that way and let y'all just see that when you check this against the answer key that, you know, that's what you probably want to do.